In this lecture, we will see what is the distortionless transmission line or the lossless transmission line. So we will continue from the last lecture we have left. So we were in the last lecture we have derived the transmission line equation, that is the Helmholtz equation. So we have two Helmholtz equation, in one for V, another for I, and these are the solution of these Helmholtz equation, and we got the solution of in this form. This is the voltage, total voltage, which is equals to the V naught plus e to power minus gamma z plus V naught negative e to power gamma z, where gamma is the propagation constant, which is complex and comprised of two parts, alpha and beta. And this part is called the incident wave or the forward traveling wave, as you have minus here. So it means the wave is propagating in the z direction. And this is the wave propagating in the minus z direction, that is the negative z axis. So it is called the backward traveling wave or the reflected wave. So this denote plus sign denote is the constant for the forward traveling wave, and this is for the backward traveling wave. Similarly, we got the solution for the current. Total current is comprised of the incident wave current and the reflected wave current. And then we have obtained this I naught also in term of V naught plus and V naught minus, and then we have divided the characteristic impedance Z naught, which is very important, and which is given by the ratio of this V naught plus over I naught plus, and which only depend upon the R, L, G, and C and frequency. So now we have these equations are in the phasor form. So we get the, now in here what we are getting this one here is the phasor form, and this is in the also in the phasor form. And when you see here, this can be written in here also, or we can write as this is V naught plus over Z naught, because we have defined this ratio that V naught over I naught plus is Z naught. So here this will become V naught over Z naught. So I naught will become V naught plus over Z naught and e to the power minus gamma Z, and here it is a negative sign. So it will be V naught minus over Z naught over gamma Z. So here you can replace here this term with the Z naught, V 1 over Z naught. This is here the, so this will be 1 over Z naught, and you will get the expression. Now to get the instantaneous expression of voltage, we have to take the real part of this Vsz into e to the power j omega t, and when we take, we get this expression. This is the instantaneous form or the time form. So again you can see here the wave is propagating in the, this part is propagating in the z direction, whereas this part is propagating in the negative z direction. And here we got the attenuation factor e to the power minus alpha z. So when it is propagating in the z direction and you multiply e to the minus alpha z, alpha being positive, then it means as you move toward the z axis, this factor will be smaller and it will attenuate. And here, because the wave is propagating in the negative z direction, so when you move in the negative z direction, this value will decrease. So attenuation will be there, will be different for different value of z, and here in this case it will attenuate when we move in the negative z direction. So rate determined by the, okay, you can read this one. Now beta is defined by 2 pi over lambda. Lambda is the wavelength of the wave, and the phase velocity, or here the simple velocity of the wave moving in the transmission line is given by simply omega over beta, and you can find that. Now special cases are here. We have the lossless line. The line will be lossless when this resistance of the wire, the transmission line, is zero, and the conductance of the dielectric is zero. Then there should be no loss. So we can see what is the expression for in that case. So a transmission line is said to be lossless if the conductor of the line are perfect, that is the conductivity is infinity, resistance will be this resistance will be zero, and the dielectric medium is lossless. So when it is lossless, the conductivity is zero. In that case, there will be no flow of current, and you can say the conductance is zero. So this is a condition for the lossless line. So for that condition, when you find the propagation constant from here, which just comes out to the j omega LC. So it is purely imaginary. So it means the alpha is zero and only there is a beta. So this alpha, which is the attenuation constant, so it is comes out to zero, and this beta, which is the phase constant, is linear function of omega. So thus, when you find the phase velocity, or simply the velocity here, and it comes out to be 1 over under root LC for the lossless line. So for the lossless line, alpha is 0, attenuation factor is 0, so it means there will be no loss as the wave propagate in positive z direction or the negative z direction. They will have the same values. There will be no attenuation, and the phase velocity is independent to the frequency, so there will be no dispersion. All the frequency will move with the same speed. So you can compare with this value for the unbounded media, where you get the equal to 1 over uh, mu epsilon. So here just you have to replace these two with the LC for the transmission line. So this is equivalent to that one. So just you have the under root LC. Now in that also case, Z naught, that is the characteristic impedance of the transmission line, is equals to under root L over C. So it will become independent to the frequency also. Once you know L and C, the Z naught will be same for the all the frequencies. So earlier Z naught is depending upon R, L and C and the frequency also. It does not depend upon the position on the transmission line. And for this lossless line, it is further independent to the frequency. So once you find the Z naught, it will remain same for the all the frequencies. So here we have three things to remember. For the lossless, the attenuation factor is 0. The this velocity is independent to the frequency, and Z naught is also independent to the frequency, and it is constant L over C. So here is the remark: characteristic impedance real. So here it is real value, and it is independent to the frequency of operation for the lossless line. Now, say next case is there is some conductivity in the dielectric, and the conductivity of the transmission line, or the conductors used, are not exactly infinity, but they are very high. In that case, there will be some resistance and some conductance in the medium. So if the conductivity of the medium is not infinite, but it is very large, so it will have some resistance, very, very small. Similarly, if the dielectric is not exactly lossless, it will have some conductivity, then it will have some conductance. So in that case, we can define a low loss transmission line where if this factor is valid, R is very, very small as compared to j omega L, and G is also very small as compared to j omega C. And this is the case when you have the high frequencies. When you have the low frequencies, they may be similar or almost same values. But as you omega is increase, then this factor will increase. So this may become valid. So this is especially the case when you are moving in the high frequencies. In that case, you can assume this one. Though R and G are finite, but once they are 10 times more than R and G, you can just use these conditions. So that we will call the low less. In this case also, it will give you the very low power, loss of the power, or the attenuation will be very small. So R and G are present. So at a high frequency, the effect is neglected. So again, when you ignore this one, you will get the alpha equals to 0 and J naught equals to L over C. Then you can put up here. So when you ignore this one, here you can ignore these two. So as compared to this one, so you get the same expression, and there again alpha is assumed to 0. This is a approximate value. We can have a more closer approximation, that is a more finer approximation. Here just you can use this expression, and you can take it out. You can write in this form. So gamma, you can write gamma in this form. You just take it out the common j omega L and j omega C, and then you can have this expression. Now you can use a binomial theorem to approximate here. So as R is smaller as compared to omega, this factor will be less than 1. This factor is less than 1. So you can approximate this expression using a binomial theorem, and you will get the 1 plus r over use half times this factor plus half, and you can ignore the higher terms. If you want to have a more finer approximation, then you can also add the higher terms. So here is a this you can ignore the higher terms. You can keep this r over 2 j omega, and this is the expression you will get. Now, when you come here, you have the real and imaginary part. If you multiply here, this will become imaginary. This will become a real part, and this has also become a. So here, when you find out the real, you can separate the real and imaginary part. The alpha is this one, and beta is omega LC. So again, alpha is some value. It is not exactly 0. There will be attenuation, and this will be smaller, and it is independent to the frequency. Beta is a linear function of frequency, and this comes out to be same as in the previous case for the lossless. So thus when you find the uh, phase velocity, then it will be just 1 over and again the root LC. So in this case, the phase velocity is all independent to the frequency. Also alpha is there. Previously alpha was 0. Now the alpha will be there, but it will be smaller. So it means there will be some attenuation in the wave, because we are saying the low loss. The losses will be there. Attenuation will be there. The wave will attenuate as it propagates in the x positive z direction or in the negative z direction. Okay, so here will be no dispersion will take. All the frequency will move with the same speed. So these are two cases. In the third case, we have the distortionless line. So in general, if you don't impose any condition, there will be a distortion in the signal as passed through the transmission line. There will be dispersion and distortion, because this when you compute here gamma. So here you have the gamma is given here. When you compute and when you open this, in this case alpha and beta will be a function of frequency, and beta will be a non-linear function of frequency. You can try yourself, open it and try to find the expression of alpha and beta. So when you open it, you will see that alpha is also a function of frequency, where beta is also a function of frequency, but it is now in general it is not a linear function, but it is non-linear. When you find out the phase velocity, then phase velocity will also become a function. So alpha is a function of omega, and phase velocity will also a function of omega. Okay, they will be different functions, but with the depend upon the frequency. So what it means by different frequency will move with a different speed, and different frequency will be attenuated differently. So alpha will be different for different frequencies. So you have two cases. One is the dispersion, which is created by this different speeds, that different frequency will move with a different speed, and they will reach the different time. So the signal will be split into time, it will disperse in time. So waveform will be dispersed. And here, because different frequency will be attenuated differently, so that will call the distortion in the signal. If you all the frequencies, for example, if you have this shape, for example, take this one, if you have some signal which have different frequency in the spectrum. So you have some spectrum. So for example, you have this spectrum up to some frequency, cutoff frequency here. There is a frequency present in some signal. When you pass, so if all the frequencies are attenuated the same factor, then what will happen? It will be somehow it will be attenuated. This you can just multiply this the what the loss has occurred, the inverse of the attenuation. Then you will again you can amplify, you can get the original signal. But if different frequencies are attenuated, for example, this part from here to here attenuated very highly, very small, yeah, very high. So it will be smaller, and there from this here there it will be somehow distorted. This is attenuated less, so it will be somehow the different part will be have a different attenuation. The shape may be different, so you may have a different shape may go something like this one. So this is called a distortion. The frequency remains same, number of frequency remains same. However, the all frequencies are attenuated differently, so shape of the signal will be distorted. Here the shape is preserved, so you can recover the original signal. But once the signal is distorted, the shape is distorted, then it will be very very difficult or impossible to recover the original signal until you use some method like equalization and other things. So distortion is a limit to the communication system. So alpha, if it will become the function of frequency, it will give you a distortion, and the velocity becomes a function of omega, then it will give you the dispersion in the signal. So two things will be there. Now to make the line distortionless, if you want to make the line to be distortionless, so in what we have the conditions here. For the distortionless line, in beta is not a linear function of omega. So what it means that different frequency will have different propagation speed that leads to the now here you will have distortion only, it will give you the dispersion, sorry. Similarly, alpha is also frequency dependent on, in general different frequency will be attenuated different, it also give the distortion. So now if you make a line to be distortionless, then that for the distortionless we will see that if you follow this condition, that is a ratio of R over L is same as a ratio of G over C, then the line will become the distortionless. And let me drive this expression. So here when we take gamma, when we have the gamma here, Rg1 plus J omega L over R and so on. So replacing C by G with L over R. So using this equation, so what you're getting, gamma is become this expression. So this is our real part and this is the imaginary part. So alpha is Rg. This is independent to the frequency. It is constant. There will be attenuation, but it will be constant. Similarly, this is a linear function of omega, that is a beta. So once you get the this, again you can have the beta same value. So beta is now the linear functions. So the Vp will become just 1 over under root Lc. This is not beta, but this is a j beta. J because j is here. Or beta is omega under root Lc. This is a j beta. Next thing, the Z naught is also independent to the frequency, and now it is just given by R over G, and R over G is same as L over C. So these are comes out to be same values as for the lossless lines. So here it will become a value similar to the lossless line. Here we have the same values as we got in the lossless line, but now alpha there was 0 now, and here it is non-zero and equals to 1. So these three parameters are same while alpha is different. Similarly, low loss transmission line, alpha is different, whereas the beta and VPRs comes up to the same. So in three cases, here the alpha is for the lossless exactly alpha is 0, low loss alpha is different, distortionless alpha is also there, it is finite. Okay. So the attenuation factor of phase velocity Vp are independent of frequency, and the condition results in distortionless line. Both Vp and Z0 of the distortionless line remain the same as for lossless line. A lossless line is also a distortion line. Why? Because for the lossless line we see that alpha is 0, it is independent to the frequency. There is no attenuation. and also the phase velocity is independent to the frequency. So we can say all the lossless lines are distortionless lines, but you can't say that a distortionless line is a lossless. Why? Because there is alpha is finite, so there will be some attenuation. So we have a table here. So this is a propagation constant, this is Z naught. So in general, this is the value of the propagation constant, this is the value of Z naught. For the lossless, alpha is 0 and beta is given by this here, and Z naught is real and given by under root L over C. Distortionless line, what you have under root RG. So these are same. So all things are same, only we have this one R case. So you can say this lossless line is also a distortionless line because alpha is 0 and these are independent to the this is a linear function of omega. But this is not a lossless line. This is a you have some losses there because due to this RG. So this is how we are the distortionless line or lossless. In communication, we will try to minimize the losses while we propagate signal on the transmission line, and we want to make the line to be distortionless because once it create distortion, it will be very difficult to remove the distortion in the line. So we will try to make the losses as small as possible and to make the line distortionless. Keeping this condition, that is the condition here we have put up here, so that there is R, there is a G there for a finite transmission lines. So you can put up this condition in such a way that it will become a distortionless line. You can change the value of L and C. So here we have some questions. So we have a lossless airline has a characteristic impedance of 70 ohm. So it is to be noted that characteristic impedance is similar to the intrinsic impedance of the unbounded media. So both have the same purpose. So Z naught and eta naught all have the same purposes there. So in this problem, the characteristic impedance is 70 ohm, that is Z naught is real, and a phase constant because it is a lossless, so it is 70 ohm. So phase constant is 3 radians per beta is given, frequency is given. Calculate the inductance and the capacitance per meter line. It is very straightforward because the lossless R and G will be 0. Z naught is under root L by C. So you know Z naught and you know beta. You know, so you have two unknowns, T equation L and C, and you can find from here. You get the form. Second equation, second problem, a distortionless line has Z naught equals 60 ohm. So this is a distortionless. So it may have the attenuation. So they given the attenuation to be 20 millinapper per meter. And the velocity of the wave is given by 0.6 of the free space velocity. Okay. And you have to find the R, L, G, and C. So for the distortionless line, we have ratio of R2 over L is same as G over C. So we have G naught, sorry, Z naught in this fashion, and alpha is this one. So what you can multiply Z naught into alpha, you will get this one R. So you can find R from here, Z naught into alpha. Once you know R, you can find the G. Similarly, you can find the other parameters. So you can go through this one. So I stop it here. In the next lecture, we will see the line impedance.